Apparently, dolphins chat it up like you and me. For the first time, researchers claim to have recorded a pair of dolphins having a conversation.
For decades, scientists have dreamed of cracking the mysterious chatter beneath the waves. Now, thanks to groundbreaking AI, that dream is becoming reality. Dolphins are finally having their voices heard, and what they're saying might just change how we see the animal kingdom forever. Join us as we unravel the hidden codes of dolphin communication, explore how AI is bridging the gap between species, and discover the astonishing messages echoing beneath the waves. When AI meets the sea.
Devices that brings that down to something that we can even detect.
While using an underwater microphone to record dolphin sounds.
Interestingly, AI has recently been used to read ancient papyrus scrolls that were buried under ash from the eruption of Mount Vesuvius. Many burnt papyrus scrolls were discovered in a luxurious Roman villa in Herculaneum, but they are too delicate to be unrolled. High-resolution synchrotron scans of these scrolls have uncovered the letters inscribed on them, allowing researchers to access the content without needing to unwrap them. Thanks to this groundbreaking work, 3 tech-savvy students earned $700,000 from the Vesuvius Challenge. With the progress in AI translation technologies, it's not surprising that there are ongoing initiatives to use AI to interpret animal communication and possibly respond to them. The Earth Species Project was started in 2018 to investigate how AI methods can be used to decode non-human communication. Since then, various projects have looked into the communication of cetaceans, whales and dolphins, elephants, crows, and parrots. Research has indicated that cetaceans and elephants have unique names for each other, while studies show that parrots learn their names from their parents and can also communicate directly with humans in our language. Chaucer, an African gray parrot, was taught by his human friend that biting is not okay. Parrots have strong beaks that can really hurt a person's finger. Every morning when Chaucer woke up, he would remind himself of this rule by saying "no nips" over and over to himself. Even though parrots have figured out how to talk to humans using our language, scientists are still trying to understand how other animals talk to each other. 60 years ago, Roger and Katie Payne recorded the sounds of humpback whales, which amazed everyone with their beautiful songs. It's said that these whale songs played a big role in the worldwide ban on whaling. If whale communication had such a huge effect, imagine what could happen if people could understand and talk to elephants. A project started by Roger, Payne's wife Katie, crows, or any other animal species. Knowing what animals are trying to say could not only give us a glimpse into the lives of whales or elephants, but could also change how humans interact with all communicating creatures. The Earth Species Project has announced that it has received a grant of $10 million from the Aphorism Foundation, along with an extra $7 million grant from Laureen Jobs' Waverly Street Foundation. Since it was established in 2018, the organization has expanded quickly, and these 2 grants will greatly improve its capacity to explore animal communication and language. While humans have always been intrigued by the idea of extraterrestrial intelligence and communication, the focus is now shifting to understanding how creatures on Earth communicate. Research on whale songs has uncovered patterns that are similar to those in human language. However, the scientists working on the whale song studies warn that they still have a limited grasp of the meaning behind these songs. They also point out that although language has typically been seen as a mark of human uniqueness, it might actually be that key elements of language are shared among various species. Dolphins have always been seen as some of the smartest creatures on our planet, and their influence is also acknowledged in enhancing health as a form of therapy. Now, in this technological era, there are amazing chances to learn about how these incredible animals communicate. This new journey is being made possible by artificial intelligence (AI) and its use by Google. Google, along with researchers from Georgia Tech and the Wild Dolphin Project (WDP), is sharing updates on Dolphin Gemma, an AI model designed to understand dolphin vocalizations and create new dolphin-like sounds. This innovative approach aims to enhance interspecies communication and expand our connection with marine life. The WDP has been studying dolphin society for decades. To truly understand any species, one needs a lot of context, and that's what the WDP offers. Since 1985, WDP has been running the longest underwater dolphin research project in the world, focusing on a community of wild Atlantic spotted dolphins, Stenella frontalis, in the Bahamas over many generations. Their non-invasive method, called In Their World, On Their Terms, has produced a rich and unique data set. Years of underwater video and audio linked with individual dolphin identities, life stories, and observed behaviors. A pod of Atlantic spotted dolphins, Stenella frontalis. One of WDP's main goals is to observe and analyze how dolphins communicate and interact socially. By working underwater, researchers can connect sounds to specific behaviors in ways that surface observations can't. For many years, they have linked different types of sounds to behavioral contexts. Here are a few examples. Signature whistles, which act like unique names that mothers and calves use to find each other. Burst pulse squawks that often occur during fights. Click buzzes that are frequently used during courtship or when chasing sharks. Knowing which individual dolphins are involved is key for accurate interpretation. The ultimate aim of this observational research is to decode the structure and possible meanings behind these natural sound sequences, looking for patterns and rules that could suggest a form of language. This long-term study of natural communication is the foundation of WDP's research and is crucial for any AI analysis. Studying the natural and intricate communication of dolphins is a huge challenge, and WDP's extensive labeled dataset offers a rare chance for advanced AI technology. At the heart of this breakthrough lies a powerful new tool, Dolphin Gemma, the AI model designed to dive deep into dolphin chatter. Let's take a look into the groundbreaking model known as Dolphin Gemma, built to bridge the gap between humans and dolphins. Dolphin Gemma, the AI ears beneath the waves.
The main use of Dolphin Gemma is to eventually look at their natural language patterns and match it with the underwater video. That's how we really figure out their language if they had it.
Created by Google, this AI model utilizes specific audio technologies from Google. The SoundStream tokenizer effectively captures dolphin sounds, which are then analyzed by a model designed for complex sequences. This model, with around 400 million parameters, is perfectly sized to operate directly on the pixel phones that WDP uses in the field. This model is based on insights from Gemma, which is Google's collection of lightweight, cutting-edge open models developed from the same research and technology that supports our Gemini models. Dolphin Gemma has been trained thoroughly on WDP's acoustic database of wild Atlantic spotted dolphins, functioning as an audio-in, audio-out model. It processes sequences of natural dolphin sounds to recognize patterns and structures, ultimately predicting the likely next sounds in a sequence, similar to how large language models for human language forecast the next word or token in a sentence. WDP is starting to use Dolphin Gemma this field season, which could bring immediate advantages by detecting recurring sound patterns, clusters, and consistent sequences. The model can assist researchers in revealing hidden structures and possible meanings in the dolphin's natural communication, a task that previously required a lot of human effort. In the long run, these patterns, combined with synthetic sounds created by researchers to refer to objects that dolphins enjoy playing with, might create a shared vocabulary for interactive communication with the dolphins. Besides studying how dolphins communicate naturally, WDP is also taking a different approach, looking into how technology can help create two-way communication in the ocean. This led to the creation of the CHAT, Cetacean Hearing Augmentation Telemetry System, developed in collaboration with the Georgia Institute of Technology. CHAT is an underwater computer that doesn't aim to fully understand the dolphin's complex natural language, but instead to create a simpler, shared vocabulary. The idea starts with linking new synthetic whistles, made by CHAT, which are different from natural dolphin sounds, to specific objects that dolphins like, such as sargassum, seagrass, or even scarves that the researchers use. By showing how the system works with humans, researchers believe that the naturally curious dolphins will learn to copy the whistles to ask for these items. Over time, as more of the dolphins' natural sounds are understood, those can also be included in the system. To make two-way communication possible, the chat system first needs to hear the mimic accurately despite the ocean noise, identify which whistle was mimicked in real time, let the researcher know through bone-conducting headphones that work underwater which object the dolphin is. Using Pixel smartphones significantly cuts down the need for specialized hardware, enhances system maintenance, reduces power usage, and minimizes both the cost and size of the device, all of which are essential benefits for conducting research in the open ocean. At the same time, Dolphin Gemma's predictive capabilities can assist chat in recognizing and identifying possible mimics earlier in the vocalization sequence, which speeds up how quickly researchers can respond to the dolphins, making interactions smoother and more effective. Understanding the importance of teamwork in scientific research, there's a plan to release Dolphin Gemma as an open model this summer. Although it has been trained on sounds from Atlantic spotted dolphins, we believe it could also be useful for researchers looking into other cetacean species, such as bottlenose or spinner dolphins. Some adjustments might be necessary for the vocalizations of different species, but the open design of the model makes this easier to achieve. By offering tools like Dolphin Gemma, there's an aim to equip researchers around the globe with the means to analyze their own acoustic data, speed up the search for patterns, and collectively enhance the knowledge of these smart marine animals. The path to grasping dolphin communication is lengthy, but the combination of committed field research by WDP, engineering skills from Georgia Tech, and the capabilities of Google's technology is creating thrilling new opportunities. Communicators are trying to comprehend the patterns in the sounds, paving the way for a future where the divide between human and dolphin communication might become a bit narrower. Unlike humans, who communicate through their mouths and vocal cords, dolphins produce sounds using their blowholes and air sacs. The noises they make can cover a wide range of octaves, with some being too intricate for human ears to detect. Researchers from Speak Dolphin shared their findings on February 25th after publishing them. They centered their study around a dolphin named Zeus, who displayed spontaneous vocalizations that caught their attention. Lead researcher Jack Kasowitz admitted that he initially overlooked it. Dolphins live in water, so their brains have evolved to process sound much quicker than ours. Researchers often find it tough to identify the rapid acoustic patterns of dolphins while recording in the field. However, once Kasowitz recognized the pattern, he noticed that the vowel sounds were different from Zeus's usual dolphin calls. Kasowitz stated that he truly believed that some dolphins, especially Zeus, were eager to communicate with them just as they were with them. Over the years, researchers have heard stories of dolphins mimicking sounds. Now they can finally study these unique vocalizations using our advanced software. Kasowitz clarified the distinction between the sounds dolphins use to connect with each other and those they make towards humans when above water. He pointed out that when dolphins vocalize above the surface, it was almost always to attract the attention of nearby humans. Zeus's vowel sounds, produced with his head above water and aimed at our research team, clearly showed how purposeful his attempts were. Weeks after the research paper was published and its groundbreaking findings, Google announced its advancements in human-dolphin communication through AI. From the technology of Dolphin Gemma, the conversation now shifts to something more organic. Researchers have also looked at a more natural approach, using human whistles as a guide to decode dolphin language. Let's take a look into the fascinating connection between human whistled speech and dolphin communication. Using human whistles to decode dolphin language. Humans communicate using whistles, and the most complex forms are often referred to as whistled languages or whistled speech because they represent a natural form of communication. The concept behind whistled speech is simple. Individuals pronounce words while whistling, which simplifies spoken phrases into whistled tunes, syllable by syllable. A remarkable feature of this whistle conversion is that it remains understandable to those who are trained, even though it uses a limited sound channel to express meaning. This method serves as a traditional way of long-distance communication, allowing people to talk across various languages worldwide. Historically, birdsong has been a reference point for studying vocal learning and language. Interestingly, human whistled languages can also help us understand how dolphins encode information in their whistles. Human whistled languages and dolphin whistles could work together as valuable testing grounds for creating new methods and algorithms to decode whistled communication signals, offering fresh insights into how information is structured and organized. Humans utilize various types of whistled systems, which can range from basic sets of codes for communication between humans and animals, or among humans, to the more complex natural form of speech, known as whistled language or whistled speech. In a human whistled language, the person sends out whistles that represent syllables, words, and sentences from their native language, effectively changing spoken language into a different sound form. This allows for conversations over long distances, as the modulated whistles enhance speech, functioning like a real telecommunication system. This whistled form of speech is a natural and ancient practice in human language, often seen as a precursor to modern cell phones. Whistled speech is a more significant alteration of the speech signal compared to shouting, which is the most common natural way languages adapt for long-distance communication. The change is much more pronounced than in other speech forms, like whispering or shouting, but the basic idea of modifying speech for particular situations remains the same. In 1963, René Guy Busnel, who was the director of the CNRZ Laboratoire d'Acoustique Animale in France, delivered an important paper at the first International Symposium on Cetacean Research. The paper was titled Information in the Human Whistled Language and Sea Mammal Whistling. In it, he suggested that comparing dolphin whistles to human whistled speech could be beneficial because the basic structure of the signals from both forms of communication was quite alike. By making this comparison, they could gain insights into how much information a frequency and amplitude modulated sine wave could carry. Busnel's research focused on how animals communicate acoustically, with a significant portion dedicated to studying the whistle communication and echolocation abilities of dolphins and other cetaceans. Importantly, he also collaborated with colleagues to publish some of the earliest monographs and descriptions of human whistled languages from various parts of the world. Among these works was a pioneering paper that detailed how the Bernese language was whistled in the French Pyrenees, another paper that introduced a multidisciplinary approach to studying whistled Turkish, and the first comprehensive book that brought together existing knowledge on whistled languages from a global perspective. At the time these publications were released, whistled languages were a little-known type of human acoustic communication, and the linguistic features had only been documented for a few groups, like whistled Mazatec in Mexico, first noted by Cowan in 1948, and whistled Spanish, which was first described by Classe. Most of the earlier studies were conducted in anthropology. Since then, research in this area has significantly progressed across various fields related to how language is produced and perceived. Naturally, the whistled communication systems of humans and dolphins differ in many ways. For instance, in how they produce sounds, the type of information they convey, their ecological environments, and the mediums they use, air versus water. On a purely acoustic level, each species exhibits unique variations in frequency range and the extent of frequency and amplitude modulation. Nevertheless, some similar acoustic dynamic features and the practical use of whistles in their natural habitats give biological and ecological significance to compare these otherwise very distinct communication systems, in line with, among others, the sensory drive hypothesis and the social complexity hypothesis. Both humans and dolphins share the trait of being highly encephalized social species that live in fission-fusion groups, with communication that is culturally learned and includes acoustic signals that convey a lot of information. Interestingly, both humans and dolphins have developed whistled communication as a way to deal with similar social and environmental challenges, that require long-distance communication in their natural habitats. Socio-environmental parallels in the study of dolphin and human whistles. When it comes to human whistled languages, there are about 8 small and isolated communities around the globe that have modified their local languages to include this unique whistled form, which they use for communicating over long distances. Roughly 40 of these communities have been researched or recorded. One of the most fascinating things about the global spread of whistled languages is that they tend to appear almost exclusively in specific types of environments, areas with mountains and lush vegetation. These ecological settings create ideal conditions for long-distance communication in rural areas because thick vegetation and uneven terrain often result in physical separation and limit spoken communication, while also putting pressure on long-distance signaling. Similarly, there are around 90 known species of cetaceans worldwide, with 40 of them being dolphin species that are still alive today. Dolphins utilize a variety of signals, including whistles, other sounds, and behaviors, to communicate during social interactions and for long-distance communication. Among humans, whistling has evolved as a way to communicate over long distances, helping people organize their daily lives when regular talking or shouting isn't enough. This is especially true during traditional activities like shepherding, hunting, fishing, and farming, where sharing important information is crucial. We don't know much about how whistled speech started, and it's still a topic of guesswork, similar to how we think about the origins of language. Today, whistled speech is mainly used for long-distance communication related to getting or providing food and other necessities in various rural areas, communities across all continents. This supports theories about how language might have originated. Human whistles and whistled speech are strong and clear signals that travel well, even with background noise and physical barriers. They operate effectively in a frequency range of 800 to 4,000 Hz, which is where humans hear best and can distinguish sounds. This narrow bandwidth helps reduce interference from other sounds, and these whistles are at frequencies higher than where most natural background noise occurs. Most noise from non-living sources is below 1 kHz, although rivers, waterfalls, and ocean waves can produce significant sounds across a wide range of frequencies, similar to white noise. Additionally, certain bird species, frogs, insects, and mammals create sounds that share similar frequency ranges with human speech and whistles. However, these animal sounds are often more sporadic, seasonal, and specific to their habitats. These characteristics form a genuine telecommunication system that is suited to natural sound conditions, allowing them to communicate over long distances using bird-like sounds, typically ranging from about 50 meters to 2 kilometers, with an average distance of 400 to 500 meters. In the case of dolphins, sound is particularly effective underwater, serving as a powerful sensory signal to detect distant objects in the ocean. For instance, Jensen et al. Used a GPS-synchronized hydrophone setup to capture the whistles of bottlenose dolphins in warm, shallow waters with high background noise, finding that their median communication range was 750 meters, with a maximum range reaching up to 5.74 kilometers. Another significant similarity between human whistled speech and dolphin whistles is that both have remained somewhat of a mystery to the public and scientists alike. For whistled speech, this is mainly because it requires specific training to be properly understood. It can easily be confused with a non-linguistic code, and individuals who haven't been trained to understand whistled speech often struggle to recognize words in their whistled versions, even if they are fluent in the spoken language. As a result, whistled human language has remained largely unknown and enigmatic outside the communities that practice it, mainly because researchers and travelers rarely identified it as a form of speech, and it still sometimes hasn't become a tourist attraction. Another reason whistled speech has stayed under the radar in many parts of the world is that this practice is found only in some of the most isolated forests and mountains, primarily among rural communities that speak some of the less common and less documented languages. Lastly, even for linguists, understanding its validity as a language can be challenging at first, because it lacks the usual acoustic features of phonemes. This is why traditional phonetic annotations struggle to capture such a significant change in how it's produced. It's also important to note that there was a reluctance among linguists to recognize and accept human whistle language as a legitimate linguistic form until the mid-20th century, mainly due to the belief that the whistled signals were too simple. However, it actually shares the same structural characteristics as spoken language, including the principle of duality of patterning. Bateau and Markley found that by using standard operant techniques, they were able to train two bottlenose dolphins, a male named Maui and a female named Puka, to react to various whistled sequences that mostly represented four-word object-action commands. In hopes of developing a two-way communication system where the dolphins could effectively use the same whistles, one of the dolphins was also taught to mimic the four electronically generated whistles. The authors concluded that a basis for the development of a language between man and dolphin has been established, supporting this optimistic view by noting that the animals learned to respond behaviorally to these complex commands, which were direct whistled transformations of simple spoken phrases by humans. Two additional findings from the Bateau and Markley study are particularly important for this paper and for understanding dolphin whistled communication. The dolphins were able to understand a command even if part of the sound of the object action word was missing. This phenomenon is known as phonemic restoration in human language. Both dolphins responded correctly when two trainers issued spoken commands that were transformed into whistles using two different electronic systems, despite the individual differences in how the trainers produced their whistles. This indicates that the information conveyed through the created words and sentences continued to exist and was shared regardless of the differences in the individual characteristics of the speaker's voices, or more accurately, what was left of this in their electronic transformation. These two aspects emphasize key characteristics of acoustic languages. Despite the many advanced technical tools that have been recently created to study bioacoustic signals, it is still unclear how dolphins perceive, break down, and arrange their whistles during interactions. We are still quite a distance from fully understanding the intricate structure of individual whistles, the timing of dolphin whistle sequences, and the potential meaning or practical use of these whistle sequences in social interactions. Sometimes one catches glimpses of potential encoding systems. In a different study, two young male bottlenose dolphins born in captivity started to imitate new computer-generated whistles on their own and use them in suitable situations. Interestingly, the dolphins began to create new combinations, forming a single continuous whistle made up of two separate computer whistles, ball and ring, and they used these while playing a new game they invented called double toy play, where they held both a ball and a ring in their mouths at the same time, tossing them into the air and catching them again. The frequency of these new combination whistles increased during the second year of the two-year study. The dolphins had never been exposed to the two whistles combined by the computer. In this instance, it was possible to identify the composite or combinatorial nature of these new whistles, giving us a hint about the possible structure of dolphin whistles. The merging or splitting of calls is not well understood in dolphins or other animals. However, there is evidence of combination calls in some other species. This has sparked a lot of interest in potential similarities between aspects of human language and the ways other species, like elephants, primates, and birds, might combine or merge their calls. Furthermore, since the dolphins weren't trained to copy the computer-generated whistles, researchers could identify which acoustic features stood out during their vocal learning. The dolphins' attempts to mimic the model sounds showed that they kept the whistle shape of the original sounds and created both exact matches of the timing and frequency aspects, as well as signals that were either stretched or squished in the frequency-time area. These findings suggest that the information dolphins encode in their whistles might be more varied and intricate. A frequent challenge in researching dolphin whistle communication and other animal vocalizations is figuring out how similar the acoustic signals are that come from the same dolphin, from others in the same social group, and from different social groups. For instance, as mentioned earlier, it was demonstrated that dolphins could spontaneously imitate new computer whistles, and their versions of the model sounds showed that they matched the exact acoustic features of the models, while also stretching and compressing the timing and frequency areas, all while keeping the whistle shape intact. This discovery highlights the significance of the contour and the flexibility of the timing and frequency aspects, and has important consequences for how researchers analyze dolphin vocal patterns. Researchers have employed time warping, also known as normalization techniques, to study whistle similarity within dolphin vocal patterns. Buck and Tyak, 1993, McCowan, 1995. Time warping methods are beneficial because they enable comparisons of signals that might differ in exact acoustic features by looking at relative changes in frequency over time. Machine learning, especially unsupervised machine learning, provides fresh insights into the parallel applications of dolphin and human whistled signals, areas where it hasn't been widely used yet. These tools have already made a significant and lasting impact on biological data processing, especially due to the early and ongoing interest from telecom and internet companies in developing speech recognition, which has made machine learning particularly influential in bioacoustics. Whistled signals are beneficial because they consist of unique curves in the time-frequency plot of a spectrogram, allowing machine learning to identify specific details of these curves or match them to templates, which is a well-established field. For instance, in the study by Gardner et al., canary whistles were examined using an algorithm that first outlined the spectrogram contours as separate curves and then utilized time warping techniques to determine how distinct a recorded song was compared to a set of templates. Given the similarities between canary, dolphin, and human whistles, this general approach is clearly applicable to our situation. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.